Okay, so today we're going to start with target 1B9. What is the difference between chemical and physical changes? A physical change involves a change in the size, in the color, the odor, a phase, but not a change in what it is. Okay? Nicole can all of a sudden start bathing with shampoo and with soap. Is that going to change her odor? Yeah. Yes, she'll start smelling nice.
Okay.
Does that change who Nicole is? Does that change her DNA? Yes. No. She can color her hair. Does that change her DNA? Does that change Nicole? No. No. She can get contact lenses. Does that change who she is? Those are all physical changes. If you change something without actually changing what it is a physical change. Now, if you change something and it becomes something new, that is a chemical change. For example, here's one that's very subtle. Boil an egg. Is that a chemical or a physical change?
Physical.
Okay, some people will say it's a physical change because it's an egg to begin with and it's an egg afterwards.
But you boil it. So
but after you boil it, my friend, can you change it back to its raw state?
Oh, no.
No, you can't. So if it's not able to be changed back, then we have ourselves a chemical change. We can change Nicole's hair back to blonde. We can put glasses back on her. She goes back to being the old regular Nicole, but did she really ever change?
Yeah.
How about if you fry a hamburger? It's a hamburger to begin with. It's a hamburger afterwards.
But you can't make it raw.
You can't make it raw again. That's a chemical change.
It'd be cool if you could, though.
It could. You could
Make
redo it if it goes. I don't know. Why would be cool? All right. How about this one? Two clear liquids are going to be added to each other. Chemical or physical? A brilliant yellow crystal forms. New thing formed. New thing formed. Chemical change. Two clear liquids all of a sudden becomes a yellow. What you would find if you could chemically test the yellow crystal is that it's a different compound. That is a solid. It will settle down on the bottom as a crystal. It is. How about this one? Dry ice dropped in water, in warm water. Dry ice is solid carbon dioxide.
Sticking in a bigger piece this time. Yep, lots of bubbles coming out. And one thing you may...
Physical, because you can take it out.
Okay, what's happening to the carbon dioxide? Is it becoming something new?
It's being released.
It's just becoming a gas. In other words, it's just changing address. It was a solid in that block. Where is it now?
In the air.
It's going in the air.
It's like a thing.
Something new? No. This is a chunk of sodium. Okay? A chunk of sodium. This is half of what table salt is. A chunk of sodium added to water.
Chemical.
Can you imagine what would happen if you were to put that in your mouth with as much water? Now think about this. Sodium chloride, table salt, is made up of that and a green gas that will kill you in a second. Put them together and now it's something you put on your french fries.
That's always natural. Yeah. That's natural.
But what happens when it undergoes a chemical change? It changes its personality. It changes its property. When sodium reacts with chlorine, it becomes something new that no longer is dangerous to us. Actually, not only is it not dangerous, it's something we need. Yes, Jeffrey.
It can be dangerous in large amounts.
In large amounts, yes. Of course. This is a strip of magnesium, tough metal. It forms a white powder that's soft. It's almost like talcum. We use it as a laxative. Magnesium is used, well, it's used in its metallic form in weaponry. It's also used as part of the surface of airplanes. But when it does this, it's used as a laxative. New properties?
Chemical.
So, if it was a chemical change, what you saw was a chemical reaction. What is a chemical reaction? A chemical reaction is going to involve breaking and forming of bonds, causing the atoms to rearrange themselves into new compounds. As I said about sodium chloride, usually the characteristics of the new things that are formed are completely different from the characteristics of the things that formed it. All right, if we're going to start describing chemical reactions, then we need to learn a shorthand because it's going to get really old using words. So we're going to use chemical symbols. What are chemical symbols? Chemical symbols are the letters, that should be letters, the letters used to represent elements. The letter or letters used to represent elements. Carbon is C, hydrogen is H, sodium is Na. Why is sodium Na? We'll talk about it later. Yes, it is based on its Latin name. Okay, there's a bazillion of them. Where can you find these chemical symbols? On your best friend's front. That's right, on your best friend's front. Here's a list. You can see the list on the side of your notes. There's one missing. Notice that 10 down in the bottom was taken out by the printer. Add 10. That list needs to be memorized by Wednesday. That list needs to be memorized by Wednesday. Yes?
I don't think I have.
Then you can download them from the Skyward, or you can come over here to a big pile of stuff that we have and look for it there. That list needs to... Now, why? Why do I ask you to memorize this? Do you know, Asher?
So we can be in the middle of a lab and not have to take too much time by learning.
That's it exactly. Now this will be the only quiz you take all year long that you will not be allowed to use your best friend. And truth is, you can always use your best friend to find these elements and their symbols. But we're going to be using these so often that it'll be a waste of time for you to be constantly referring to your best friend. These are things that you probably should be able to do automatically. So I'm going to ask you to memorize, I think there's 26 or something like that. It's not that many. And you really should already know most of them. All right, if chemical symbols are the letters of the chemistry world, what are chemical formulas? Nope. More like the words. See, chemical symbols are the letters. Chemical formulas are the words. A chemical symbol, a chemical formula is going to tell you two things. It's going to tell you the elements involved, and how many of each element is involved in the form of a subscript. The elements involved and how many of each element is involved in the form of a subscript, a little number that's below the formula, the symbol. Here's some examples. Carbon monoxide, deadly gas that's produced from the incomplete combustion of hydrocarbons. Odorless, colorless, you can't tell, and it'll rob you of your breath. It's literally breathless. It'll kill you. A lot of people die from carbon monoxide poisoning. Sugar, C12H22O11, those are subscripts there. That 12, that 22, that 11, those are subscripts. In order for it to be sugar, it has to be 12 C's, H22O11. The salt they add to roads is calcium chloride. It's not sodium chloride. It's calcium chloride. KNO3 is one of the major constituents in gunpowder. Okay, so let's see if Serenity gets it. Chemical symbols are the letters. Chemical formulas are the words. What are chemical equations? Yes, the sentences, the chemical sentences. They describe what you begin with and they describe what you become. They describe what you begin with and they describe what you become. What do we call what is used up in a reaction? Reactants. What do we call what is produced in a reaction? Here's an example of a chemical reaction. This big number is a number that we're going to use. Oops. This big number is a number that we're going to use in order to obey the most important law in chemistry. That's the law of conservation of matter. I'll explain it to you later. It's called balancing equations. I think you probably tried it in middle school. Here are the subscripts. Isn't it odd that hydrogen and oxygen have these little 2's beside them?
No.
Well, actually it kind of is because the other elements do not. If it was helium, or if it was molybdenum or chromium, they wouldn't have these little numbers by them. We'll talk about it. Give me a second here. What is a molecular structure? Molecular structure is not something we're going to deal with until later, but another way of describing a chemical formula is through its molecular structure. It describes not only what the compound is made up of, but what it looks like as well. This semester, we will be mostly concerned with just chemical formulas. What it is. What is it made of? Next semester, how it looks is going to be more important to us because how it looks will be able to explain some stuff. For example, water kind of looks like that. If you were to turn it around, it almost looks like Mickey Mouse with the ears. Here is hydrogen chloride and ammonia, stinky part of Windex. Boron trifluoride, carbon tetrachloride is used to dissolve things, and methane is natural gas. Those are structural or molecular formulas. All right, let's get back to this twosome. There are 7 elements that in nature do not ever exist as a single. They're always a couplet. Think of them as the 7 twins of the periodic table. You know how it's just, a twin is actually a rare thing, right? Well, in the same way, there are 111 normal people, and 7 of them are twins. There is an acronym to help you remember this. We imagine that there was a Catholic priest. His name was Brother Huncliffe. Brother Huncliffe. That was his name, Brother Huncliffe. Brother Huncliffe. And Brother Huncliffe's name actually, coincidentally, helps us to remember the 7. They are bromine, hydrogen, oxygen, nitrogen, chlorine, iodine, and fluorine. If you do not want to memorize them, and I would recommend you do, if you look on your best friend's butt, about in the middle, maybe a little bit to the right of the middle, you will find the list there. See it, M?
Oh.
I did ask M, but that's okay. Nicole, see it in the middle? A little bit to the right of the middle?
That?
Well, that's the other right.
Okay, right, yeah.
There you go.
Whatever, how you say it. That's his, right? Something molecule? Diatomic.
Here they are.
Oh.
Those are the twins. You need to remember that they are the twins. Later on, they will be important to us.
Who are the twins?
The 7, Brother Huncliffe's. What are some examples of the electrical nature of matter? Ever experienced static cling during the winter months?
Yes.
Girls, have you ever gone to school with a skirt that's stuck with something plastered to your skirt or something like that?
No.
That's static cling. How about this? Have you ever, during the winter months, you have carpeting at home and you constantly shock yourself?
Yeah.
Okay, so 1800s, they started realizing that matter was made up of positive and negative things. And they started coming up with rules for these positive and negative things. One of the things they realized is that positives and negatives attract each other. Positive particles don't like each other at all. And negative particles don't like each other at all. Isaac, remember that you can download these PowerPoints, print out the notes. That way you're not killing yourself trying to copy these notes down. This was pretty much fleshed out in the 19th century. They did not recognize them as being subatomic particles or things that atoms are made up of. They thought atoms was the smallest thing possible. But it was an understanding of these negative and positive particles that led us to understand that, nope, there are things smaller than an atom. Positives attract to negatives. Positives repel each other. Negatives repel each other. What do we call the positive particles now in the 21st century? Protons. What do we call the negative particles now in the...
Electron.
What is a neutral atom?
A neutron.
Where
No. Yes.
Where the number of protons and electrons are balanced.
What does neutral mean to you? It's neither positive or negative, right? It's neutral. Okay? So if it's neutral, Jeffrey is absolutely right. An atom is going to have equal numbers of protons and electrons, making it neutral. Neutral. A neutron is a different particle that's in the atom. In the 19th century, they had not discovered the neutron. So a neutral atom will have equal numbers of protons and electrons. So, what are ions?
What?
Positively or negatively charged atoms.
These are atoms that have either lost or gained electrons, making them, as Jeffrey said, either positively or negatively charged. Because either they have too many negatives or not enough negatives. There are two types of ions. Positive ions and negative ions. Positive ions, we're going to call them cations. This is how I remember. I know it's kind of silly, but it's just the way I remember.
Oh, wow.
It works.
I know, because the I's are positive. Negative ions are called anions. They have too many electrons. So you either don't have enough electrons or you have too many electrons. Electrons are the key to the whole thing, Devon. All right. For example, what are the ions that make up sodium chloride? It's one sodium ion, one chloride ion. Here it is. They form these beautiful cubic, perfectly cubic crystals. Here's a diagram of one. Notice that they're different sizes, but when they combine together, they always combine together in the same ratio. And the way they pack in together makes it so that they form a perfect cube. All right? Here is a half-life fan.
I see zombies in the distance there, but I also notice what looks like an ionic lattice, a sodium chloride ionic lattice, right in front of us. Notice the chloride ions that are negative are electrostatically attracted to the sodium ions, which are positive in this distinctive pattern. Now, ionic bonds are very strong, but if you add energy to them, you may weaken those bonds by giving them more energy than the bond energy, and the ions may become free. And these freely moving ions have different properties, which we'll get into later. Alrighty, I'm getting a little scared the zombies are moving in, so I think I'm going to hop in my hovercraft and splat right through them. Those four there look good enough.
A very violent form of chemistry, but you saw the sodium chloride crystal there. All right, so what does it mean to be a positive one ion? So if you're a positive ion, you lose or gain electrons? Lose. So if you're a positive one, like the ones we encountered in the lab yesterday, you must have lost one electron. What do you think it means to be a negative one ion? Gain an electron. That's right. Yesterday we encountered such things that were positive 2 or negative 2. What does that mean? Positive 2? Jackson? No. What does positive 2 mean? Ash, go ahead, Jackson.
It takes like 2 of something to get.
Nope. Positive. Positive means you are more positive than negative. So what did you, if you're a positive ion, did you lost or gain? Jackson, if you're a positive ion, did you lose or gain electrons? Lose. So if you're positive 2, you lose 2 electrons. Very good. Asher, if you're negative 2, what has happened to you? You have gained 2 electrons. You have gained 2 electrons. Let's see if I can't find trying to find a periodic table for you. I will just make one. Take out your periodic tables if you haven't done so already, because we are going to tattoo it. All right. I want you to come up here to the very top, and I want you to place a +1 on top of hydrogen. A +1. Now I want you to go to the next column over and place a +2 on there. Those are the elements that tend to lose 2 electrons. Come over here, and there should be a line. Just make it darker. That is your dividing line between the metals and the non-metals. Everything to the left is a metal. Everything to the right is a non-metal. So let's go over to the non-metal side. F. Do you see F right here? Put a -1. Next over, -2. Next over, -3. And that's only till you get to the line. Everything to the right of the line is negative. Everything to the left of the zigzag line is positive. All right? +3, +3, +3, +3, +2, +2, asterisk. We'll deal with the asterisk here in a second. +1, +2, +1, +2, +4, +2, +3. I'm just going to write them. You need to tattoo your own periodic table. Now yesterday you had that orange chart that was so useful. Now you have your periodic table. You don't need the orange chart anymore, at least for the monatomic ions, the one atom ions. Are we good? Got them all? You'll need those. Now those will become critical to you. If you put any other tattoo on your periodic table, then I will take up your periodic table and give you a fresh new one, and you lose that critical pieces, those critical pieces of information. So do not ever write on your periodic table unless I tell you to. All right, let's deal with mercury. Put down here Mercury 1 is going to look like this. And then Mercury 2 is going to look like this. Mercury 1 and Mercury 2, especially Mercury 1, is an odd duck. We will deal with it later. It does look like it's switched. All right, we good? So, what is the most important rule to remember when dealing with ions? You do not gain or lose protons. You only gain or lose electrons. So, what are ionic compounds? Ionic compounds is the result of when things that want to lose electrons combine with things that want to gain electrons. And they combine together in just a way so that everyone is satisfied. If, for example, Jeffrey's the type of person that only likes to lose one electron, and Gracie's the type of person that wants to gain 2 electrons, can Jeffrey satisfy Gracie? No. He's not man enough to satisfy Gracie. What is Gracie going to have to do? Find another man. Another man that can only give 1 electron. But now, both of those will be able to satisfy Gracie. But what if Gracie ditches Jeffrey and finds a man that can give her 2 electrons? Then she only needs that 1 man. So, ionic compounds are formed by ions, well, atoms, really, that will lose or gain electrons within themselves in order to be completely satisfied. And yesterday you saw a little bit of that. Sometimes they were just satisfied as man and wife, right? Sometimes it was man, wife, wife. Sometimes it was man, wife, wife, wife. That's okay. Sometimes there was wife, man, man, man. Right? It's whatever it takes for everyone to be satisfied. How are these guys named? How are they named? The metal's name is first. Don't mess with the metal's name. Okay? In most marriages, not all, in most marriages, does the man's name change in any way? No. In the same way, the metal's name does not change. What about in most Western, American? What happens? The last name of the girl changes. Well, in the same way, you must always take the non-metal and end it in IDE. The non-metal's name ends in IDE. So, let's see if we can get these. You're going to need to find them on the periodic table. Devon, you want to handle the first one? Very good. Sodium, that's the metal. Don't change his name. Chloride, that's the non-metal. Her name used to be chlorine, right? But you changed the ending to IDE. Emmy, how about the next one? Find magnesium. It's always, the metals are always first, so find it on the left side of the zigzag line.
What'd you write for the first one?
Sodium chloride. Magnesium. And N stands for, look for it on the right side of the zigzag line. Well, good. Nitrogen is the girl in this case, but girls' names are changed to what? Okay, nitrogenide. Actually, it's nitride. Nitride. All right, Jackson, you want to tackle LIS?
Lithium sulfide.
Lithium sulfide. Very good. And Emily.
Is it aluminum oxide?
Very good. Aluminum oxide. Aluminum oxide. Any questions on these?
How do you spell aluminum? Aluminum? Yeah.
Look on the periodic table.
I'm trying to find it. I can't.
It's on the left side of the zigzag line.
Oh, it's like right. Oh.
How do you write chemical formulas? Well, we learned how to do that yesterday. Here's some rules. All you have to do is write down the key words, right? Do so quickly. Place the positive ion first with the correct charge. Place the negative ion symbol second with the correct charge. If you see a Roman numeral, the Roman numeral will tell you which of the two charges you're dealing with. Balance out the charges just like you did yesterday. All right. Who would like to try the next one? Barium oxide. No, somebody new. Thank you, Randy. Barium. Find it on the periodic table. Give me the symbol. Give me the charge. It's a metal, so it's going to be on the left side of the zigzag line. Second column. Ba. Charge. No, sir. Charge. We tattooed those. Randy. +2. All right. Oxygen. It's a non-metal, so look for it on the right side of the zigzag line. Charge. Okay, look at their charges. Do they satisfy each other? Yes. So the charges cancel out. Your final answer is BaO. Good job, Randy. Potassium fluoride. Hunter. Potassium, metal, left side. Look for it. Give me the symbol. Give me the charge. Fluoride. Right side, non-metal. Give me the symbol. Give me the charge. Do they satisfy each other? Hunter? Excellent. They satisfy each other. Then that means their charges will cross out, and your final answer is? KF. All right, those were easy. Who would like to do a harder one? Thank you, Bailey. Bailey, aluminum. Look for on the left side. Charge. Oxygen on the right side. Do they satisfy each other, Bailey? Who has the advantage? Okay, so oxygen's not woman enough for him. So what is he going to do? Okay. Now is everyone happy? Nope. Who's not satisfied now? Aluminum's not No, aluminum is satisfied. Oxygen isn't satisfied. So what does oxygen ask aluminum to do? Ask another for another. Al plus 3. Now is everyone happy? No! Who's still not happy now? Aluminum is plus 6. And oxygen is? -4. Bailey only. Okay, so there's too many positives, right? Not enough negatives. So what must happen now? What? Plus 6 minus 4. It's not even. Who's not satisfied? Okay, so aluminum asks oxygen to do what? Now it's satisfied. So what's the total? These cross out. That's not part of the total. Those, we have now successfully crossed everyone out. So what's the total? Al2, O3. Very good. Benny, Ben, Ben. Ben, Ben. Benny, Ben, Ben. Ben, Ben. Strontium, metal. Look for on the left. Second column.
Oh, that's hard.
Charge. Chloride. Look for it on the right.
Yeah.
Charge.
Yeah. Fine. Okay.
Are they satisfied? Who's not satisfied?
The SR.
Too many positives, right?
Right.
Can't take away positives. You can only add electrons. So, all right. So,
So you add it.
what happens to the charges now?
They're even.
Total.
SR, CL. 2.
SrCl2. You realize you did this yesterday, right? But you were using the little thingies. You need to be able to get to the point where you do this. Well, we're doing it without the little thingies, but even this is too much time. You need to be able to do it in your mind. In your mind. Okay. What are polyatomic ions? They're groups of atoms that together form an ion. Who's ever been to Costco or Sam's? Okay, what's the key thing about Costco or Sam's? They come in bulk. Okay, you can't buy one box of Kleenex. You buy a package that has 20 boxes of Kleenexes. Okay, so if you have a large family or you have a business, Costco is it. Okay? Think of polyatomic ions as these package deals, where you're not buying one, you're buying a whole package of these things. So they are groups of atoms that form together and they create an ion together. They are a package. Leave them alone. How do you write chemical formulas for the polyatomic ions? The same as regular formulas, except if you have more than one of these packages, what do you need? If you have more than one of these packages, you need parentheses. If you have more than one of these packages, you need parentheses. Now, yesterday, you found these package names and their symbols on that orange sheet that I gave you. You won't have that orange sheet. As soon as you finish copying that down, look on the back of your periodic table. What? Yes, look on the back of the periodic table. Above 6 o'clock, what do you see? There they are. The most popular are there, the polyatomic ions. Those are all packages. Notice their numbers. You don't mess with those numbers. You never, ever, ever touch those numbers. They are a package. They've been pre-packaged. At Costco, you can't buy a Kleenex. You can only buy packages of 6. You can't say, okay, I only need 10. I'm going to buy a package, and then I'm going to break the next package, set aside 2, and buy only 4. What are they going to do to you? No, they'll make you buy the whole thing. You can only buy them by packages. All right. Barium sulfate. Let's see. Tanaya. Barium. Look for it on the left. Second column. Sulfate ends in ATE. If it was an element, Tanaya, it would have ended in IDE. By the fact that it ends in ATE means don't look for it on the periodic table. Look for it on the back. Incorrect. That's sulfite. All right. Do the charges, is everyone happy? Do the charges cancel out? Scratch the charges out. Final answer? Very good. Very good. Nicole, you get the hard one. Magnesium, look for it on the left. Hydroxide ends in IDE, which means it's probably an element. Look for hydroxium or something like that. You're not going to find it. Look on the back. There's a few polyatomic ions that end in IDE, and hydroxide is one of them.
OH, -1.
Okay, so that's a package. That's a package. If you want, you can circle the package in order to remember that it is a package. Circle the package. All right, Nicole, are these charges equal? Then somebody, you don't have enough of somebody. Who is that somebody? Okay. Now, is it equal?
Yeah.
Do the charges cross out?
Yeah.
Final answer. Very good. You see, gang, if you were to write a 2 here, what would it look like?
Look at those 2 hydroxide.
It would look like it's 2 hydrogens and 1 oxygen. But really what you have is 2 of these packages. So how do we show in chemistry we have 2 packages? Notice we didn't use parentheses here. Why? Because there was only 1 package. There was not any confusion. It was only 1 package. Here, we needed parentheses because we had multiple packages. So, how do you write chemical names involving polyatomic ions? Oops, sorry. We have a few more. Aluminum sulfite. Spencer. Aluminum, I'd look for it on the left side. Charge. Should have been tattooed on it. You didn't get that tattoo? No.
+3.
+3. So fight, I-T-E, Spencer. It's not in the front. Okay. We've seen this before, haven't we? Where it's 3 and a 2, so how do we balance everything out? Will that fix everything? Now you have too many negatives, so what do? Too many negatives, not enough positives. Oh, you screwed it up. Now you have too many positives. So what do? Now does everything cancel? How many pluses? Plus 6. How many minuses? Final answer. How many ALs? Very nice. Very nice. Finally. You want one, Serenity?
What?
How about letter D? Sodium. Look for it on the left. Left of the zigzag line. Those of you who were not here for the great tattooing of your periodic table, you need to get a neighbor's and tattoo your periodic table. Emily, if you don't mind, lend yours to Isaac. Periodic table, okay. All right.
Sodium's Na+1.
Na+1. All right. Peroxide ends in IDE, which means it's probably an element, but you're going to be really disappointed in that it's not there. So look for it in the back. You have a question, Jeffrey?
Yeah, why does it say peroxide up there while on the paper it says phosphate?
I'm sorry. Just change it to peroxide.
Oh. Okay.
Sorry. I like peroxide better.
What are you saying, peroxide on Earth?
Yes. All right. So what's peroxide?
O2 -2. O2
That's right. And is it balanced?
No.
How do you fix it?
Add an Na.
Now is it balanced?
Yes.
So final answer?
Na to O2.
Very nice. Very nice. Good job. All right. How do you write chemical names involving polyatomic ions? You don't change the name to IDE. Just write the polyatomic ion as is.